This lesson deals with Supplemental Problem 216. You can find this problem in the course ebook in the Chapter 2 Supplemental Problem starting on page 18. Given this circuit, could you solve for the current I sub S, I1, and I2? There's a lot of ways you could do that. I'm going to use equivalent resistances to solve for it and then do power in the circuit to show the conservation of power. Let's find the resistance seen by this voltage source, then we could solve for I sub S just using Ohm's law. I have 3K in series with 6K because they share the same current, so that's going to be 9K, and that's going to be in parallel with 18K. Combine those two. The product of 18K times 9K over 18K plus 9K turns out to be 162K squared over 27K or 6K ohms. That's in series with the 4K. I have a total of 10K. So I've reduced this down to just one loop where I've got 12 volts across the 10K. The current would just be, by Ohm's law, 12 divided by 10K or 1.2 milliamps. Now, knowing the current coming out of this voltage source, I can go back to one of our previous steps where we found the equivalent resistance between terminals B and D and found that to be 6K. Well, if that 1.2 milliamps flows into that 6K, we would have then the product of these two, the K's and the milli cancel, and we'd get 6 times 1.2 or 7.2. Could also do a voltage divider of 6K over 6K plus 4K, which would be 6 divided by 10 times 12, which is also 7.2. Now, going back to the original schematic, now they know that this is 7.2 volts, I can then begin to solve for the voltages around the remaining loops here. So I got 1.2 milliamps entering. The current that's in here is 7.2 divided by 18K, and that's 0.4 milliamps. And that's what I'm also trying to solve for, but I'll put that in engineering notation as 400 microamps. But I have 1.2 milliamps here and 0.4 leaving, so this has to be 0.8 leaving. We could do the formal Kirchhoff's current law. One of our answers we're looking for, so that would be 800 microamps. Now let's use this information and find all the voltages and all the currents in a circuit. I do this a lot when I'm consulting on a circuit that's pretty complicated. Let me see what's going on in the circuit. So I know that the current coming out of here is 1.2 milliamps. Multiply that by 4K, and you get 4.8. K's in the milli cancel. We knew this was 0.4 milliamps and 7.2 volts, but this current being 0.8 times the 3 would give me 2.4, K's and milli cancel. And then likewise 0.8 times 6K would just be 0.8 times 6 or 4.8. Let's make every element absorb power. I'll show the current in this direction going in the plus terminal, which would be the opposite of 1.2 milliamps, so minus 1.2 milliamps. Look around the loops here. The rise in voltage equals the drop, so 12 is equal to 4.8 plus 7.2. Go around the loop this way, 7.2 is equal to 2.4 plus 4.8. Or go around the outer loop, 12 is equal to 4.8 plus 2.4 plus 4.8. Right-hand side equals the left-hand side. Let's find the power absorbed by each element. Current entering the plus terminal is a minus 1.2 milliamps. The product with the 12 volts is minus 14.4 milliwatts. The resistor, just take the voltage times the current, and I get 5.76 milliwatts. The voltage times the current for the 18K is 2.88 milliwatts. The voltage times the current for the 3K resistor is 1.92 milliwatts, and then lastly, the voltage times the current of the 6K resistor is 3.84 milliwatts. When you add all this up, it's equal to 0. Even though we didn't use these properties to figure things out, that's true for every circuit at every instant in time. Whether it's wireless, digital, analog, this is true for every circuit. If we take the power absorbed for each element and have only power absorption, it will sum to 0. And this is Supplemental Problem 2.16.